As we go on now to topic 3 of chapter 2, this is set operations. And as we look over on the side, we see a number of key vocabulary words that we'll be building on as we go through this section and useful for other sections. The intersection of sets, the union of sets, the difference of sets, ordered pairs and their use, Cartesian products. We know Venn diagram already, but we're in operations with Venn diagrams. And then a new vocabulary, De Morgan's laws for sets. So as we start off, we're looking at two candidates, candidates A and candidate D. Now, as a voter, you're wondering, who should you vote for? And what are the points of their platform that you like, that you would support? So we have honest me and determinarian. Okay. Now what we're going to do and look at their platforms in which this person will spend less money, and we're going to call that M for money. This candidate also will spend less money, and we'll call that M, that point in their platform. Now, honest me wants to emphasize traffic law enforcement, so we'll use the T to represent that. And he will also increase service to suburban areas. We'll call that S. Now, determinarian is going to crack down on crooked politicians. We'll call that P for politicians. And his platform element would be to increase service to the city as opposed to suburban areas, so we'll call that C. Now, both candidates, as you see, are going to spend less money. That was one of their planks in their platform. But the other areas are different. And how could we illustrate this using a Venn diagram? Well, we'll move it up and show you. So in our universe of the Venn diagram, we have T and S and M for, we had a quick flashback there, but for honest me, this would be his set within our Venn diagram universe rectangle, and determinarian has this. Now notice there is an area where the platforms overlap, and that is where we put what is found in both platforms. That is the letter M, that they will both spend less money. Now this illustrates what we call, and we'll see it here defined, the intersection of sets. Now when we write this, there is a formal way using roster notation to say this would be the amine set, and this is the Darien set, and we're looking for their intersection. This symbol right here, this sort of an upside down U, is the symbol for intersection, and the results of this is the letter M. This is what is found in both sets, and in a Venn diagram how it is illustrated. So now the general rule here and the general diagram, and another flashback, is that we have set A, set B, and the portion that is intersecting is what we have a member in each of the two sets. So this is read the A intersecting with B. X is such that X is a member of A and X is a member of B. Remember, we could also use the word element there. Okay, and often it's illustrated in this general way. Here you see it in a specific way. Now, when we go to our textbook, they often give us a little aside examples. And if you take the primary colors of red, blue, and green, and you start intersecting them, the intersection of the three colors give you white. I remember doing that little lab when I taught general science. Okay, so let's look at some examples now. And again, don't look at the answers, but see if you can pick these things out. So here, for letter A, we're looking for the set of intersection. So it'll be this one intersecting with that. Well, this doesn't have a 3 here, but it does have a 4, so 4 is a point of intersection. Doesn't have a 5, 6 is 1, 7, 8. So these are our only members that intersect between these two sets. Now for B, a similar thing. We have 9, we don't have a 9. 14, don't have a 14. 25, don't have a 25. 30, we don't have a 30. So in this case, we leave it like this, or we can put a circle with a slash to indicate that it's an empty set. And for letter C, now since this is an empty set and these contain these 3 elements, there are again none in common. So as they indicate here, the intersection of an empty set with something is an empty set. Okay, but again, when you do your homework and study plan, you're going to have to do these on your own. This is to give you some immediate practice after we review a topic. Now, looking at figure 6 here, we see that the universe is the rectangle. Here we have set A, set B, but there is no intersection. When there is no intersection, we give it a special word. We say these are disjoint sets. So again, I would think in your notes you'd have a little picture of this and the word describing it. So in a disjoint set, set A and B are disjoint if there is no intersection. That is, the intersection is an empty set. That's what it looks like in a Venn diagram. Now when we do the union of sets, this is often, again, the picture is illustrated by everything is colored in. So you would take everything that would be in set A and everything that was in set B, and if it were repeated, The M is in both sets. We only write it once. And this is how it would look. That is the union of sets. When you combine all elements, and if they're repeated, you only write it once. And we should mention the symbol to indicate union is this special U. So the union. Okay, let's go on. So in writing you would say A union with B. X is such that X is a subset of A, or X is a subset of B. Or all the members of X are in A, or all the members of X are in B. Now in example 2, these are pretty straightforward. You're just going to include all of the elements and don't repeat them as you write them. And often, if it's alphabetical, you put them alphabetically. And if it's numbers, you put them in ascending order. And these are the answers. Okay, now, if it were just that easy, this would be a very easy thing. But now we are looking for unions and then of complements. Now these are the things that are not in the set. If we review just a little here, we said if set A, then everything outside of set A is the set complement. And words are okay, but a diagram is better. So there's our area of interest. This is our universe. This is set A. And its complement, that is everything outside of set A, is A prime, or A complement. The complement of A. Now, again, you need a strategy of how you are going to do these. Knowing what's there is important. The universe is this. Set A is this. Set B is this. And set C is this. So our first question is A prime in union with B. Now, first we have to identify what are the elements in A prime. Well, in A prime, what are the elements in A prime? Well, we see A is 1, 2, 3, 4. So of our universe, 1, 2, 3, 4 is this. So what would A prime be? What's the complement of A? Well, it would be the things that are not in A, which would be 5, 6, 9. So we are defining our complement, A prime. Now we're going to produce union now between this and B. So we look and say, well, not union, I should say, intersection, right? So this is A prime, and I could write this out, but there is what B is. B is 2, 4, 6. There's 2, 4, 6. So now, what do we find in intersection? And I have to be careful when I say those words. And the one that's obvious is 6. So the results of letter A then, the only thing would be 6 And the strategy we used for it was first to define what was the complement of A, this, which was everything that's not in the regular set A. And then we listed B, and we're looking once again, upside down U is intersection. Now I might mention that a little later on we're going to say that intersection is associated with a key word mathematically, and that is the word and. Just to introduce that, we'll be using that later, but the word and, when they're working officially with sets, that indicates an intersection. All right, let's look at letter B. Now here we're going to look at what is the complement of set B and the complement of set C, and whatever they are, we're going to put them in union. So how do we figure that out? Now set B itself is 2, 4, 6. So the complement of B would be 1, 3, 5, 9. And that's what they're showing right here. Now, what is the complement of C? Well, C is 1, 3, 6, 9. So C is 1, 3, 6, 9. So what would the complement of C be? Well, it would be the 2, the 4, and the 5. And that's what we list right there. So now we have written B prime, the complement of B, and C prime, the complement of C, and we want union. So we put these all in one roster. And that's the answer. But it took a little while, just so you know how to figure it out. Now, using that same methodology, for letter C, we want to define our A, which is listed right there. We then want to define our B, which is listed there. And we want to define our C prime, which we did earlier. And hopefully you have it in your notes, which is actually right here too. Now, you know all of these. What would be the intersection now? And you know that this is what this is, and there is your set A now, intersection with this new combination, and you see them highlighted in blue very nicely. It will be 2, 4. Now notice, this is what you're going to find a lot as we move along in this chapter, and particularly the next chapter too, where they're asking you to follow a recipe. You need to know what the recipe means. You'll have your values, and then it's just grinding them out. In letter D, we see an easy part. We want a union of B and C. There's set B, there is set C, there's the union. But they now want what is the complement of that. Well, notice in our original set, we don't see it here, but what is missing from this was the 5. So this prime, the complement of this, is 5. An interesting note, and I think probably a good time to mention it, is that when you see this in parentheses, it is not the same as the complement of B in union with the complement of C. And we'll investigate that a little later. Now they're giving us a little food for thought here. As we look at comparing properties of numbers, in many traditional algebra courses and in math courses, they'll review the properties of arithmetic that allow us to move forward and accept things in mathematics. Well, we say that if A, B, and C are real numbers, that is, they're on our number line, we have what is called the commutative property of addition, which states that if you add A to B, that's the same as adding B to A. This is that we can just switch them around in addition, and that is the same. That's the commutative property of addition. Now, we have a commutative property of multiplication too. We're not using it right now, but it would be AB equals BA. Now, there is an associative property as well. If we have the letters A plus B plus C, we know that equals A plus B plus C. These are the exact same order of all our variables, and we're just adding them together. One side equals the other side. But in the property, associative property, we're saying we could group these two together first, add these two, then add the C. Or we could add the B and the C together first, then add the A. Again, order is the same, we're just associating them differently. And in mathematics they say this is always a true statement. So it does not change the value. Now another one we have is called the identity element for addition. That is, you can add 0 to anything and it doesn't change its value. Now we have the identity property of multiplication. We can multiply anything by 1 and it doesn't change its value. They're not giving us this here, but just as a little review of things. And then what is the identity element for multiplication? Well, we did that. Okay. There's also what we call a distributive property, where we're going to multiply, and since there's some addition in the middle, we say over addition. So it's A times B gives us AB, and then A times C gives us AC. This is the distributive property. We can distribute. Now the reverse of this is we can factor out the letter A. So in this direction it's the distributive property. If you reverse it, we call that factoring. Okay, so if we had time we would do some group discussion on this, but we'll pass that up for now. Okay, here we have the symbols. What would this mean in words? Well, it would say this set might be described as the set of all elements in A that are also in B but not in C. The not is what implies the complement of C. If it were in C without the prime there, then you would say or in C, but it's not saying that. It's saying those that are not in C, that is C complement. And for this one, the set of all elements that are not in A, because that's A prime, the complement of A, or not in C, that is the union of the two, that intersects with those that are not in B. Again, prime indicates the complement, those that are not in the original set B. Okay, the difference of sets. There are times when what is said here is just what we want to say, so let's just read it together. Suppose that set A is equal to this, the numbers 1 through 10, and B, the even numbers 1 through 10. If the elements of B are excluded or taken away from A, this results in set C. C is called the difference of set A and B. And the picture of it would look like so. Remember, some members are found in both sets, but when we take away those members in set B, all of the elements that are in set B, even the ones that were found in set A, that gives us the difference of the set A and B, which we're calling set C. And then in writing, it looks like this. Set A minus set B, X is such that X are the elements of A, and X are not elements in B. So all of the B elements are taken away. That's the difference of sets. Now they give us some interesting things again as we're looking at the textbook. They're saying another way to say this is A intersecting with the complement of B. Here we're going to look at some of the things we had already and understanding what they're asking. So here, where the difference of sets A and B, here the difference of sets B and A, and here we have A and B from this letter A here, but we want it to be with the union of C complement. So we would have to find out what makes up C complement. And again, the work is shown here in some detail. There is set A, right there, minus set B, and you end up with this as your answer. In B, you're reversing that. There is set B first that we're going to take away from set A. And we might say, wow, now there are no members left. So that would be an empty set. And again, from our first answer, right there, we're going to find the complement of C, C prime, which is this, after we go to the universe and take this away from it, we're left with this. And then now we have this and this. We end up with union of this. Again, we don't want to make our lesson too long, but the information is right there, and you will be getting examples like this so you can follow what they're asking. Now, as we look at ordered pairs, there is a difference. The traditional ordered pair, we put a parenthesis. We're talking about the X element and then a Y element. This is an ordered pair with parentheses separated by a comma. Now, in an ordered pair, is the order significant? That is, does this equal Y comma X? And the answer is no, it does not equal. So order is significant. Now, this differs from what we said if a set contained, now here we're using braces, a 1 and a 5. Order, we said, was not important. So this is a major thing, a major definition about ordered pairs and roster notation. Remember, in roster notation, we use braces, and the order of the elements are not significant. In mathematics, when we use an ordered pair, we use parentheses, and order is significant. And we see this illustrated here. Again, a quick note is, if you have the ordered pair A comma B and C comma D, they are equal providing that the A's and the C are the same and the B and the D are the same. So let's get some true-false statements. So here we have a 3, comma 4. This is an ordered pair. So when we look at this, is this another way of saying 3? Yes. And this another way of saying 4? Yes. So this is true. Now here, these are roster notation, and in a sense could be sets. Did we say that order was significant here? No. So where they're saying it's not equal, they are equal. So this is false. And now these are ordered pairs, and we said the order was important. So this is false. Okay.